All right, so Unit 3 exam review here, guys. Big thing about Unit 3. So far, you're probably feeling very confident about how well you're doing in this unit, and that's good. I want that confidence to continue into the final or into the unit exam. What I do not want to do is for that confidence to evolve or morph into overconfidence. Okay, if you are right now thinking, yeah, I just, I got 100% or almost 100% on that circular motion assignment, I've got 100% on all my quizzes, and I'm rocking this gravitation assignment so far, I don't need to study. Holy crap, could you not be more wrong? Okay, if that's the attitude you go into your preparation for the exam with, you won't like what happens. If you go into your exam preparation, okay, with some vigor, okay, and take it seriously, all right, and spend some time on it, then you will be happy with how the exam goes. Okay, yeah, I'm not going to show you anything that's much different than what you've already been doing, but here's what you have to remember about what you've already been doing. You haven't been under a time limit. You've been able to ask questions, work with your friends, okay, or see the questions ahead of time. It is different when they are all fresh on the unit exam. That's the important thing to remember. Okay, yes, you've been able to do things, but you have to think about, okay, how many times did I get stuck on something and then somebody gave me a little tip that got me through it? Or I asked Mr. Coderre and he gave me a little tip that got me through it. Or I had enough time that I could sit there and look at it for a half an hour and then I finally figured it out. Okay, those are not options, obviously, on the unit exam. Okay, that's where the unit exam can feel different. Okay, and I just don't want people to approach it overconfident. I want you to approach it confident, because you should be. You're good at it. Okay, but I want you to approach it confidently. Okay, don't take it for granted that you're just going to do as well as you've done on everything else. Exams are always a little different. Okay. All right, first thing we talked about in Unit 3 was uniform circular motion. We talked about how it happens, okay? We talked about centripetal acceleration, centripetal force, okay? We talked about the principles of circular motion in general. There will be multiple choice items. That means I should have said many multiple choice, not multiple choice, because that implies that you have A, B, C, and D, and they are related to 1, 2, 3, and 4 underneath. Have you ever seen a question like that? It's horrible. Okay, you get them in university all the time. A multiple choice question. So the first 3 are like 1 and 2, 3 only, 5 or whatever, and then underneath is the list of other answers. Yeah. Oh, it's brutal. Yeah, it's brutal. Right. Or they give you what you think is going to be an awesome test, true or false, except it's right minus wrong. Yeah. So they mark all the ones you got right, and then they subtract from that all the ones you get wrong, and that's your mark. Oh yeah, yeah, it's horrible. Okay, because you think true or false, I can't do wrong on that, except that you can, and it can go really poorly. All right. Anyway, you don't have to worry about those. There will be many multiple choice items about the principles of uniform circular motion. So, what are the principles of uniform circular motion? Something undergoing uniform circular motion is traveling at a constant speed, but not at a constant velocity, which means it is always accelerating because its direction is always changing. Acceleration can only be caused when there is a force. Right. What kind of force? A centripetal or net force. Okay, remember that our centripetal force in this unit is our net force. Okay, those are the principles of uniform circular motion. Okay, those are the things that we have to remember. Okay, because they will be tested in the multiple choice for sure. Okay, so we got constant speed, changing velocity. All right, we've got our, remember that centripetal acceleration is v squared over r, okay, and that Fc is m times that, which is mass times acceleration, which is how we calculate net force. Okay, those are the things we have to remember in terms of just the principles of it. Okay. As examples of uniform circular motion, we talked about the 2 curves. That's mass times centripetal acceleration. Okay, we talked about the 2 kinds of curves. We talked about unbanked curves. What holds you in an unbanked curve? Friction. Is that something you'll have to remember? Yes. Okay. And we talked about banked curves, right? And curves that are banked are using a component of the normal force to push you back towards the center. Okay. Purpose of a banked curve is that we can do what with it? okay, maybe we can go faster, but more likely it's right. It will be safe at a certain speed regardless of the road conditions. Okay, I will be able to negotiate that corner even if it was covered in perfectly frictionless ice. Okay, there would be a speed at which I could negotiate that corner and not slide in or out of it. For banked, yeah. Obviously, for an unbanked curve, if it's frictionless, you're screwed because friction is what provides the centripetal force for an unbanked curve. Yes. Yeah. So the one out here where it's like 40 or 60 or whatever it is. Okay. I don't remember what it is. I don't know. I just kind of take it and I know kind of how fast to go. That's really bad. I'll remember to check the speed limit sign the next time. No, no, it's not 30. Yeah, to go to Deerfoot, I think it's 40. Yeah. Okay. So on that one, that's 40. We think, okay, and we take it at that speed because that's what we should do. We would, even if it was really, really slippery, like we had freezing rain and it was just a sheet of ice, we wouldn't slide in or out. Okay, we'd be able to go around as long as we went 40. If we went 60, then we would slide into the guardrail. Okay. All right. So for unbanked curves, we have to remember that the force of friction is what provides the centripetal force. It's what keeps us from sliding in or out of the curve, well, mostly out of the curve in this case. Okay. So if FC equals FF, then we have to set those two formulas equal to each other if we're involved in any problem solving to do with an unbanked curve, right? What's the formula for the force of friction? Right, normal force times mu, and since it's an unbanked corner, normal force equals Fg, right, the force of gravity, right, because it's unbanked, so when it pushes down on the ground pushes back with a force equal to gravity, right? So that's what we're looking at here, okay? Mu mg, okay, is mv squared over r. Okay, this diagram here goes with the bank curve explanation, so that's, if you're looking at that, it goes with the next one. Okay, any questions on unbanked curves? You guys haven't seemed to have any trouble with those, so that's good. Well, on an unbanked corner, you can't fall into the middle. But if you go off to the side, there's not enough friction to overcome or to keep you in that radius of a curve. So you would slide outwards until you got to a radius of a curve that there was sufficient friction with, which usually doesn't happen because once you start to slide, you go from static friction to kinetic friction and you're off the road, right? Like it just happens too quick. If you had, a huge parking lot and you were going around and around, you started to slide, you might actually get out to a radius where, yeah, okay, or you'd slow down enough as you slide that you'd be able to negotiate a turn again. All right, for the banked curves, okay, remember that this is the diagram that goes along with banked curves. A banked curve is an inclined plane. Whatever angle we bank it at is the angle here, right? Gravity acts straight down, and because we're going around the corner, we push on the corner. That makes normal force actually greater than the force of gravity. Okay? Because not only is it overcoming the force of gravity, but it's also having to respond to our inertia. When we push on the road has to push back, okay? And that creates a horizontal component that is directed back towards the center of the circle that provides a centripetal force, okay? You will not have to derive the formula for a banked curve, but you will need to understand how a banked curve works, because there could be some multiple choice questions about the mechanics, which is what I just explained, of a banked curve. No, Fn is not Fc. Okay, this is what we did. Okay, in order to derive that formula, okay, so I'm just going to kind of redraw that diagram here. We got force of gravity this way. We've got normal force this way. So these two things are the two forces, okay, and then we've got kind of their vector sum. Actually, sorry, I drew that wrong, but okay. So we've got Fc being here, right? So this angle, right, is dependent on the opposite side and the adjacent side. With me there? Okay, so I've got mv squared over r equals my opposite side. Sorry, I don't have mv squared over r, I have Fn. Okay, so I've got the opposite side sine of theta, okay, over the adjacent side cos of theta, okay? And what I have there is mv squared over r, that's my opposite side to the angle, divided by the adjacent side, okay? What's opposite over adjacent? Tan. So the tan of theta equals mv squared over r divided by mg, which leaves me with the m's cancel, and I have v squared over rg. That's where we got that bank curve formula from. Okay, we related that the angle that we have to bank a corner at is dependent on gravity, because that's what gives us some of the normal force, the radius of the curve, and the speed at which we're traveling, most importantly, because the faster we travel, the harder we push on the corner. Yeah? Okay. Okay. All right, so that was that messy derivation right there. But as long as you understand that it's the bank of the curve that gives us normal force, a component of that acts as a centripetal force, that's the mechanics of a banked curve. Okay, that's what we need to understand for that. Okay, and then we talked about artificial gravity after that. Okay, so to generate artificial gravity, we need to have a spinning drum, and we need to be standing on the inside of that spinning cylinder. Okay. If we're standing on the inside of that spinning cylinder, then our inertia wants us to leave the cylinder. As a result, we push on the inside of the cylinder, and the cylinder pushes back towards the center, okay, giving us a feeling of weight, okay, that isn't actually weight but feels like it, right? So as a result, we have a centripetal force that is equal to the force of gravity, or some fraction of the force of gravity. If it's not spinning very fast, it might be 1/2 mg, okay, or 1/4 mg, or if we spin it really fast, 2 mg, okay, or something like that. The question might specify you're spinning it fast enough to feel like it's normal, then it would just be Fg. If it says to make it feel like it's 1/3 of normal, it would be 1/3 Fg. Okay, everybody follow there? We didn't do very many like that, but that does apply. Okay, so what's happening here is our inertia wants us to go this way. Okay, the cylinder prevents it and pushes back with a force that feels like gravity, okay, and could be numerically equal to gravity. All right, and then we can set mv squared over r equal to mg, and then we go from there. All right. All right, so that was all the stuff we talked about to do with uniform circular motion, where the speed of the object moving in the circle didn't change. Then we moved on to vertical circular motion, which is non-uniform. Okay? In vertical circular motion, the speed of the object does change because now gravity is speeding it up and slowing it down as it moves through the circle. So some things we need to understand for the multiple choice and check your understanding kind of questions, okay, are where in the circle would I feel lightest, heaviest? Where can certain conditions be created within the circle? Like a feeling of apparent weightlessness can only be created where? At the top, inside or outside, but at the top. Okay, at the bottom, I'm going to feel the heaviest because that's where the forces oppose each other the most, and I have to be pulled back into the middle the hardest. Okay, so those are things that we have to remember. Okay, the big rule we have to remember about vertical circular motion in terms of problem solving is this one. Fc is the vector sum of all forces. That means it's the forces in minus the forces out. Yes, if I go just fast enough to stay in the circle, so I'm traveling at the minimum speed, I would feel weightless there because I wouldn't push on the track, and the track thus wouldn't push back, right? You wouldn't notice it as much as you would going over the top because you're already upside down. Yeah. Okay, so the places we talked about, okay, were the top of the vertical circle. If I go over the top of a vertical circle, I am generally going to feel, well, not weightless, but lighter. Okay, there's not a situation where I can go over the top and feel heavier. Okay, there's no situation where I can go over the top and feel heavier. Every situation will either be feel normal or feel lighter. Okay, to the point where I might experience a feeling of apparent weightlessness. right? If I'm going under the top of the vertical circle, that is where there is a minimum speed. There's no minimum speed for any of the other spots, okay? But there is a minimum speed for the inside. If I don't go fast enough, I will fall out, okay? If I go just fast enough, then I won't push on the track, so there'll be no normal force. There'll just be the force of gravity, okay? All right, so remember, Fn is apparent weight, okay? Normal force is also termed apparent weight, so if you're apparently weightless, Fn is 0. Little things to remember, terminology things, so you don't get caught up on the test with terminology, okay? If a question says you're pulling 3 Gs, how much heavier than normal do you feel? 3 times, which is why Fn would equal 3 mg. Okay, so if you're pulling 3 Gs, you feel 3 times heavier than normal. Okay? Again, terminology, just stuff to be ready for in case the question uses those terms. Okay. And then we talked about the bottom as well. Okay, the bottom is where you would feel heaviest because gravity is pulling you out. Your inertia wants you to leave the circle tangent to the circle. The normal force of the circle has to push the hardest there to overcome those two things. That's where I feel the heaviest, where I'm most likely to black out. Okay, things like that. Okay. So should you expect a vertical circular motion problem on the test? Yes. Definitely. Yeah. Okay, then we talked about gravitation because that was the end of the first half of the unit. Vertical circular motion was the end of the circular motion part. Then we talked about gravity as a centripetal force for the remainder of the unit. Right? So we talked about Newton's universal law of gravitation. Things to understand about Newton's universal law of gravitation. The force of gravity is always mutual. Okay? I am just as attracted to the Earth as the Earth is to me. The force of attraction between us is mutual. All right? It's not the Earth pulling on me, it's us pulling on each other. Well, we don't really give a direction because it is a mutual attractive force bringing us together. It's like tension, okay? Like that. And if it said, what's the force of gravity from my perspective, then I would say down or towards Earth's center. But in general, it doesn't say that. It's a mutual attractive force. Okay. So what are the things that can affect the gravitational force between two objects? Okay, the mass of the two objects and the separation distance between their centers. Okay, is that relationship proportional or exponential or some other thing? Yeah, radius is squared in that formula, right? So if I double the distance the two objects are apart, I will feel 4 times lighter, right? 4 times less attracted, okay? It's important to remember that that's the relationship between those, okay? All right, so force of gravity is mutual, okay? Force of gravity is calculated by going G times mass 1 times mass 2 divided by R squared, right? You could end up with a question like this, let's say. Okay, so we'll just walk through one like this. I want to find the net gravitational force acting on the Earth right now. Okay, I want to find the net gravitational force acting on the Earth. How many forces of gravity are pulling on the Earth right now? 2. Okay, the force of gravity between the Moon and the Earth, and the force of gravity between Sun and the Earth. Okay, can I calculate them both? Yes, I can. So what I would do is I would first go force of gravity between the Sun and the Earth, okay, and I would say 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, so mass of the Earth, times 1.99 times 10 to the 30, mass of the Sun, divided by 1.50 times 10 to the 11 squared. Okay, that's the radius of the Earth's orbit, or distance from center of Earth to center of the Sun. Okay, everybody with me there? What do you suppose people will screw up on this calculation? They'll forget the square. Happens all the time. All right. So when I do that, okay, I'm going to have Just a bracket. All right, so the gravitational attractive force between the moon and the earth is 3.528 times 10 to the 22. All right, now what do I do? Right, find the force of gravity between the moon and the earth. Okay, so that'll be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 7.36 times 10 to the 22 divided by 3.85 times 10 to the 8 squared. Okay, so I've got mass of the earth, mass of the moon on top, for average earth-moon distance on the bottom, and it's squared.
Is this assuming that they're all in a perfectly straight line?
Yes. Yeah, I would, like, if I had a question like this, the diagram would look like that, where they're all in a straight line.
But there would be one where you'd have to do like a vector sum.
No, I probably wouldn't make you do an angled one. The big deal with this one on angles is that even when the moon is all the way out to the right or left-hand side, its force of gravity is so much smaller than the sun's that it makes like a fraction of a degree angle on the force. So it's not even worth doing because it's like 0.05 degrees. Like it just, yeah, it makes the earth wobble, but not like a huge amount. Okay, all right, so now I've got, sorry, I don't have that number yet. Okay, so we've got 6.67, negative 11, 5.98, 24, 7.36, 22, divided by 3.85, 8 squared. All right, so we're looking at 1.98 times 10 to the 20. Okay, so we're talking hundreds of times less, okay, gravitational force between the moon and the earth as there is between the sun and the earth, which is why the earth orbits the sun and not the moon. Okay, all right, so we've got that, and okay, now I want to find the net gravitational force acting on the earth. Okay, so this is from the earth's perspective. So this number is towards the sun, and this number is, which is also towards the sun. So what am I going to do with those two numbers? I'm going to add them up. I'm going to calculate the vector sum of all forces and just add them together, and that'll give me like 3.53. I don't think it changes it very much. Okay. Oh, brackets. Oh, 3.55 times 10 to the 22 newtons towards the sun, because it's a vector quantity, okay, would be my final answer there. That's my net gravitational force acting on the earth, with the earth and the moon in that position.
So if the moon was like, let's say, straight above it, would you just do like
Yep, exactly. Okay, that's what David was asking just a minute ago. Come on. So I would have, if the sun was here, earth was there, and moon was here, okay, then I would have the force of gravity between the sun and the earth, and we already calculated that number, and then on the head of that, okay, be the force of gravity between the moon and the earth, and this would be F net, right? Now, that's not to scale. If I drew that to scale, the force of gravity between the sun and the earth is the length of the screen, and the force of gravity between the moon and the earth is a little thing this long you can't even see me draw, right? Like it just doesn't make any difference. Okay. Everyone okay with that? I would say so, because then it would be pulling it in the opposite direction, right? Okay, that sort of makes sense. Your question on your assignment from yesterday, question 10 with the four masses, is kind of like this. Okay, except it's got vectors in it because you got a downward force, a force to the right, and a force 45 degrees below, right? Okay. So that could be kind of what you might get for a universal gravitation question, okay, something like that, because obviously I'm not going to give you a problem that's just, hey, plug into Newton's universal law of gravitation. I know you guys can do that. You need something a little bit more challenging than that. Okay, so like we said, net gravitational force, and oh, look, there we go. There's the sun and the moon and the earth or something. I don't know, okay, something like that. Okay, then we talked about satellite motion. Okay, what provides the centripetal force in satellite motion? Force of gravity. Okay, so in satellite motion then, we always have that Fc equals Fg. Okay, and that's big Fg. Big G times mass 1 times mass 2 over r squared. It'll depend on the situation. If the question says it's orbiting at this altitude, then I have to add the radius of the Earth to get the distance center to center. If it says calculate the altitude, I can't do that. I have to find the radius first and then subtract the radius of the Earth. Okay? So yeah, it depends on the situation. All right, so remember these are the key words, okay? Really about the only way I can trick you with a satellite motion question is to play the height, surface, or altitude trick. All right, so be on the lookout for those terms because they mean you're either adding or subtracting the radius of the orbited body. Okay. Also remember that you may have to substitute, okay, into that formula. So having to substitute 2 pi r over t, okay, means substituting in for v, right, and squaring it all and doing that. Okay. So just remember that that could come up on a problem-solving item as well. Okay, in the multiple choice, basically I'm just looking at the fundamentals of satellite motion. Okay, what provides the centripetal force? Does the mass of the satellite matter? Okay, things like that are going to be kind of checking your understanding of how satellite motion works. Okay, the other part of that is Newton's thought experiment. Okay, about the cannonball and how you make something orbit the Earth. Okay, something can orbit the Earth as long as the distance it falls is equal to what? The curvature of the Earth, right? Okay, not the distance it travels, right? The distance it travels is going to be determined by how high above the Earth it is, right? As long as the distance it falls is the distance the Earth curves away, it never gets any closer to the Earth because the radius won't change. Okay. All right, okay, and like we said, having to do that substitution, okay, is going to be something important there. Then we talked about gravitational field strength, okay? Remember that gravitational field strength is different than the force of gravity. Okay? Gravitational field strength is the rate at which the objects move towards each other, not the force pulling them, towards each other. Okay, so be able to solve problems with that formula. The biggest stumbling block for people is not identifying that a question is a gravitational field strength question. Okay, even when in bold-faced, italicized, and underlined font on the question it says gravitational field strength. Okay, make sure that you're on the lookout for that. Right. Okay, and then don't forget about Kepler, right? There's a possibility that there could be a question on the unit exam that could be solved using Kepler, right? Maybe I give you the right information and you have a choice between solving a question about a planet orbiting the sun with Fc equals Fg or with Kepler, okay? In that case, you pick whichever one you're most comfortable with, right? You get the same amount of marks regardless of which way you do it, okay? But just know that there is a possibility, of course, that you could get a question that is solvable both ways. It doesn't have to be. That's the nice thing about Kepler is the units for period can be whatever I want, right? It could be years, days, seconds, weeks, doesn't matter, okay? And radius, as long as whatever I have is matching, you can do whatever I want, right? So it could be meters, it could be kilometers, it could be astronomical units, light years, right? Yeah. Probably wouldn't use light years because that's really far, but. Right. 1 astronomical unit is the distance from the center of the Earth to the center of the sun, which is why we always use Earth as the second body if we're talking about something else orbiting the sun. Yeah, because it's 1 year over 1 AU. Okay, so the test. The test has 15 multiple choice questions. Right, and we've talked about how those are going to be just check your understanding kind of questions. There are no calculations in the multiple choice. Okay? They are all checking your understanding of the principles of circular motion, gravitation, satellite motion, that kind of stuff. Okay, and then we have 7 written response. My feeling on this test after I made it was I should put another question on there, and then I forgot to. This test is short, like really short. Like I really feel like I should have put another question on it. It's that short, okay? Because when I made up the key, I was done making the key in 13 minutes, which is really, really short, okay? So yeah. So we got, your questions here, like we talked about. You're going to have some uniform circular motion questions, banked curves, unbanked curves, okay? Stuff on gravitational field strength, vertical circular motion, satellite motion, universal gravitation, artificial gravity, okay? The things we talked about already. Right? There's no surprises on the test. You've done questions like everything that's on here multiple times. 44, which is like 9 marks or 11 marks shorter than your last test, which was 56 or 57. Okay, so yeah, this is really short. Okay. No, the whole test is out of 44. Yeah. None. There are no part A, part B questions. Yeah.
Are there like significant digit?
Possibly. There's always going to be something like that. So yeah, make sure you remember your significant digit rules. Okay. The big thing being, if a question doesn't give you anything except constants from your formula sheet, then you can use a reasonable amount. Okay, or basically go with what was on your formula sheet, I would say. So, I think everything on your formula sheet is to 3. Okay, I would go with 3 then, but in the end, there can't be a wrong answer in terms of significant digits if you're only using the numbers from your formula sheet. Okay. In your notes, yeah. Okay. It's not really definitions per se, it's here's a situation, how does what you know apply? Yeah. All right, and yeah, I think that's it. Yeah, 8. Oh, this must have been for a previous version. See, yours has 7. See, I told you I should have had one more question. I should have put another one on there. See, when I built this one, okay. Well, I'll get you on the next one. Next one's gonna be really long.
It had more questions, but it was only 30.
No, 33 marks in the written. That's what it's saying. Okay. Okay, so I'll take questions from you guys. Anything you want me to cover in a little more detail?
Can we try something like number 10 on this?
We did. That was the Earth-Moon question. Okay, when I showed you at the moon off to the side, that's what that is. Okay, so it's just net force, right? You know how to add vectors together, put them tail to head. That's what you got to do, right? It's vector sum of all forces, tail to head. No, there's no way for me to give you a question that could only be solved using Kepler's law. Well, I guess there is, but I wouldn't do it. Okay, the way that would be, I gave you like a question about moons around Jupiter, and you don't have any of the masses on your formula sheet, and I say, okay, the Io has this orbital radius and orbital period, calculate the orbital radius of Europa if its orbital period is this much. Then you could only solve that using the information in the question, and you could only use Kepler there. I totally don't see myself doing that. Okay, if I'm going to give you a question, it would be solved both ways or only using satellite. It wouldn't go the other way. Okay, where in the circle? Bottom. Okay. This is probably a bit easy, but okay, it's still a vertical circular motion problem. So we are dealing with the bottom of the vertical circle. Gravity is pulling out of the circle. Normal force is pushing into the circle. Okay. Fc equals forces in minus forces out. Okay, my force in is normal force. Force out is gravity. And I'm looking for their apparent weight, which means I'm looking for which force? Fn. All right, so what do I do with Fg? Add it over the other side. All right, so I'm going to have mv squared over r plus mg equals Fn, and then I'm just plugging in my numbers. Okay, so we'll have 65 times 19 squared over 12. Okay, so that's m times v over r. And then I'm adding that to 65 times 9.81. Okay, so their apparent weight would be 2,593 newtons. It's a lot. It's very heavy. Yeah. Yeah, it's 4 Gs. Yeah. It's about what you're going to feel at the bottom of the mind bender. Okay, bottom of the loop on the mind bender, about 4 Gs. What's that? Lots of times. Yeah. Yeah. Lots of people black out on the mind bender.
So if we're looking on the circle and apparent weight is this
Yeah, Fn would be 0. So I wouldn't ask you to find Fg because it's just mass times gravity. I'd ask you to find how fast it was going or what the radius of the circle was or something like that. Yeah.
when you're using Kepler, the radius around the sun. Does that mean just now like
You can't use Kepler in that situation. They're not orbiting the same thing.
okay, so that's
Yeah. They have, yeah, the only way you can use Kepler is if the two objects have the same orbital center. Yeah, that's why you can't use it for a satellite orbiting the Earth and then use Earth as the second object because Earth does not orbit itself. At the top on the outside. Okay, so that's the only situation where that would apply because if I'm going over the top of the vertical circle, okay, and that's why I'm saying like don't try and memorize when an Fg is minus Fn or the other way around. Remember this, forces in minus forces out, and then draw the diagram. Okay, so at the top, gravity is in, normal force is out. So this would be a situation where I'd have Fg minus Fn. Yeah?
Can you try
Unbanked or banked? Unbanked. Okay. I don't know how this one's going to work out because I just picked the numbers out of my head. We might get a ridiculously large or small coefficient of friction here. Okay, so we have an unbanked curve, okay? And usually in an unbanked curve question, if you accidentally forget what's providing the centripetal force, the question will usually remind you because it either has to ask for coefficient of friction or has to give it to you, okay? Anytime you're given coefficient of friction, you know friction is a force that's involved, okay? So we've got Fc equals the force of friction, so that'll be mv squared over r equals mu times the normal force, which on an unbanked corner is gravity, okay? And we are looking for mu in this question, so we would divide both sides by m times g. Okay, and remember we talked about this the day we did banked curves. V squared over rg equals mu. V squared over rg also equals the tan of theta. It always equals the thing keeping you in the corner. Okay, so when we plug in our numbers here, we've got 16 squared divided by 70 times 9.81. All right, so yeah, okay, 0.37, okay, would be our coefficient of friction. That's actually a bit slippery. Sorry, there's no units on coefficient of friction. 0.37, okay, is our coefficient of friction there. All right, now the trick with this question would be significant digits. How many? 2. Why not 4? Yeah, you never used the 1500, it canceled out and it never got plugged in. Okay, the 1500 kilograms was a mass and it didn't end up affecting the answer because it was a canceled value. Okay. All right, what else? A bank curve, okay. Okay, so we're looking for the speed at which a frictionless banked curve can be taken if its radius is 200 meters and its bank angle is 9.5 degrees. I didn't want to have an answer with one significant figure, so I made it 9.5. Okay. All right. So for a bank corner, the tan of theta equals v squared over rg. That formula will be on the front of the test. Okay, it's not one that you have to memorize or derive on the spot. Okay. So I'm looking for V, so that means I'm going to multiply both sides by R times G, okay, and then square root to get V. So we got 200 meters times 9.81 times the tan of 9.5. All right, so 18 meters per second would be our maximum speed for that one.
Would you have to ever use tangent?
If you were looking for the angle, right? So if you're solving for theta, you'd have V squared over RG inverse tan. Okay, what else, guys? Yes. Artificial gravity, yep. Okay, so it could be something like this. Okay. We're looking for the radius of the space station if it's spinning at 15 meters per second and makes people feel like they're at home on Earth, right? So in other words, the centripetal force provided by the spinning drum is going to feel like gravity here, right? Which means mv squared over r equals m times g, right? And I'm looking for the radius. So I would multiply both sides by r, divide both sides by m times g, and I'd be left with r equals v squared over g. So that would be 15 squared divided by 9.81. All right, so it would have a radius of 23 meters. Okay, so all artificial gravity questions work the same. It's Fc equals Fg, and you're just solving for one piece or the other. Yeah. Okay, what else? Okay, yesterday I did post the review package in Google Classroom. Okay, so if you're looking for sample questions and tips and stuff, what things to look over, read over, whatever, okay, it's all in that review package on yesterday's posts. Okay, so you can have a look at that as well. Okay, that's good. You guys had lots of questions. Okay, took up almost the entire period. It's awesome. Okay, that's the way it should be. Okay, so that is going to happen, guys, obviously on Wednesday of next week. Tomorrow, I'll be starting Unit 4, so I'll be talking about simple harmonic motion tomorrow, and I'll be talking about simple harmonic motion on Tuesday. Okay, Wednesday will be your test. Okay, Thursday we'll go over the test and continue on with simple harmonic motion, and then Friday we'll do a lab on pendulums. Okay, and then, holy smoke, the next week we're going to West Ed. Right, so it's all coming up pretty quickly. Speaking of West Ed, are there any more permission forms for me? Okay, I need, guys, those permission forms by Tuesday. My letter home to your parents said Monday, but I have zero intention of being here on Monday to collect any. Okay, so I'll give you a day's grace and make it Tuesday, the 21st instead. Right, if you have still not given me your permission form or paid the fee, okay, please make sure that that happens by Tuesday so that I can tell West Edmonton Mall how many tickets we're going to need. Also, if you are missing any assignments in any of your classes, especially this one, those need to be in by Tuesday. Otherwise, I won't be ordering you a ticket. Okay, so make sure you are all caught up and you have no NHIs. No, you may not.